So work problem number 3 on this page 420 odd, 23. This particular one is about Newton's law of cooling, which is often used when things cool down, and it's an exponential decay function. If I look at it on autograph, we can see it looks a bit like this, plotting the general exponential decay function. And what this is saying is that it's decaying from some start point. Okay, so this exponential decay function, which is here, I've plotted the general exponential decay function. So that means it's starting off at 1. In other words, the whole amount at the beginning. So the temperature at the beginning, theta 0. So it's assuming theta 0 is 1. And then what happens, as something cools, it starts off cooling rapidly because the difference in temperature between that point and room temperature is large, at its largest. So it cools rapidly to start off with, and as it approaches room temperature, the rate of cooling falls off until the temperature is room temperature. So this 0 is in fact going to be the ambient temperature. Okay? And because the rate of cooling depends on the temperature above the ambient temperature, that's an exponential function. It's something where the rate of change of it depends on how much there is a classic exponential function. So that's what's going on here. It's an exponential decay. An exponential decay. Theta 0 is the start temperature, and this K will be dependent on the material, whether it's copper or wood or something like that. The rate of cooling also depends on the material. So the excess temperature means the excess temperature above room temperature. At time 0, at 0 time, is theta. So this represents your theta 0. Determine the rate of change of temperature after 40 seconds, given that theta 0 is 16 and k equals negative 0.03. So we can put some values into the function and then differentiate it. Why are we going to differentiate it? Because we're after the rate of change of temperature, which is the gradient. So as soon as you see rates of change, which means we're after the gradient, then you're differentiating. Okay? So I'm going to take my function, put in the values. So theta equals theta naught, which is 16, e to the minus k, which is 0.03 t. And then I'm going to differentiate it and find out what the rate of change of temperature is when t equals 40 seconds. So which rule do I use to differentiate, and what's the answer? So differentiating, we get d theta by dt equals negative 0.48 e to the negative 0.03 t. The power doesn't change. The number just goes down and multiplies by the number in front. Now, after 40 seconds, we can find the rate of change of theta with time, and that equals negative 0.48 e to the minus 0.03 times 40. And now just plug that into a calculator, and out comes the answer. Would you like to try it and see what you get? So it comes out to be negative 0.14 degrees C per second. That means it's negative, means it's cooling, so we'd hope it was going to be negative. 0.145 degrees centigrade per second. Okay? And if we wanted to just confirm that on autograph, we could go to autograph, go to 40 seconds on here, and then or if we wanted to confirm that value, we'd have to plot the differential function and see that it's 0.1, whatever it was after 40 seconds. Okay.